So let's wrap up our notes here for chapter 3. Today we're going to talk about residual plots. And a residual plot is a scatter plot of the regression residuals as the y variable versus the explanatory variable as the x. So we're actually making a scatter plot that uses the residuals that we can calculate. We talked about residuals yesterday. That's where you take y minus y hat. So we take those residuals, we make those our y variable, but we use the original x's from the original data. And the good news is our calculator automatically finds and stores all of those residuals for us every single time we do a linear regression. So when you run stat calc 8 and you get the regression equation and you get r and you get r squared, the calculator automatically stores those residuals in a list. Now here's the key. You have to run that linreg stat calc 8 with each new set of data. So honestly, my advice would be to get in the habit of always doing stat calc 8 when you put in a new set of scatterplot data. Otherwise, once you've stored one list of residuals ever, like the first time we do this in a few minutes, you're going to have a list called resid in there. But if you don't rerun stat calc 8 with the new data that you're using, you're actually going to get old residuals trying to pair up, and you're not going to get what you want. So the residuals are automatically saved for us in a list that the calculator titles resid. And so here's the first key to kind of fill into your notes, that when we want to make a residual plot, we're going to use L1, our original L1 is the X list, but we're going to use resid as the Y list. And in order to go find that list resid, we press second stat and then arrow down to resid. It's kind of like when we recalled those two other lists. So let's practice this right now. Practice making a residual plot. If you don't already have the arm and height list in your calculator, why don't you go back in your notes and pull those up, or if you have them saved, you can pull them up. I have mine right here. So here's my arm list, here's my height list. And if I had just entered these in, I would want to make sure that I went out to a blank screen and then ran stat, arrowed over to calc, and then I want to use number 8. And then right now I want to make sure I run it with list 1 and list 2, because those are my data lists. And I'm going to hit calculate just like we did the other day. Now, does it look like anything new's happened? It's the same equation we looked at yesterday. It's the same r and r squared we had from before. But now I know for sure that I have the right lists saved. I have the correct resid list. When I want to go make a residual plot, I'm going to go to second y equals, just like we did before. And I want plots 2 and plots 3 turned off. I only want to make one scatter plot at a time. I'm going to go into list 1. Now, this is exactly how we had it set up before when we did a plain scatter plot. But I want to make a residual plot now. So I'm going to scroll down and I'm going to leave the X list as L1, but I want to change this Y list to resid. And to get that list resid, I'm going to go to second, then stat, and I'm going to have to scroll down until I find a list called resid. And there it is, and even if you deleted it, the calculator would automatically create it again the next time you did stat calc 8. So I'm going to hit enter. Now I'm making a scatter plot using list 1, my x's, or list 1 is my x's, and resid is my y's. That's what I wanted. So then I can now do zoom 9, and that is my residual plot, which right now just looks weird to you, and that's fine. What we're going to talk about next is what to look for. But that is a residual plot, and that is how you make it. If you ever needed to look at the actual list of residuals, sometimes there are questions that ask something about what is the largest or the smallest residual. One way, and I don't think it's as good, but one way to do it is to hit the trace button. And trace will let you arrow around from one point to another. The problem is it doesn't go from left to right in the screen, it just works its way down the list. And so it can be kind of hard to compare. Like if I was trying to figure out which of these was lower, it's kind of hard. You have to kind of just keep jumping around until it eventually gets there. So I think a better way, if you hit stat and then enter and go up to a different list, I don't want to mess with list 1 or list 2, but if I put my cursor up on list 3 and then pull up that resid list, so go to second, stat again, choose resid. What the calculator does is actually dump all of the residuals right in there. And now it's much easier for me to look at, all right, if I want the largest residual, I can actually see their values. And largest residual doesn't have to be positive, but I think that 8.1 is our largest, yeah. So our largest residual here would be 8.1537. And the thing I like about this way too is if they asked you what is the largest residual and what data point did that come from, we've got the data point it matches up with right next to it. So you don't need to do that every time we do a residual plot, but if they ask you about specific residuals or which has the largest residual, that's how you do it. For setting up a residual plot, the only thing you have to do is change that Y list to resid. So now that we've made a residual plot, what's the point, or what does that tell us is the next big question. So if all is well with the regression line, meaning if we will go to graph some data and the form appears linear, and it actually is linear, then the pattern in the residual plot will be an unstructured band of points centered at y equals 0. And this one's a very ideal one where they are really evenly scattered across. The one that we have here isn't seem as perfectly balanced, but there are no alarming things in this residual plot. And so once you look at it, if you decide, yep, I don't have anything strange going on, this appears to be a scattered group of points centered at y equals 0. That's the line going right through the middle. This is what we would say. We would say in this residual plot, the residuals are scattered with no curved pattern. And then we could say, in terms of what does that mean or what does that tell us, we would say a linear model seems to be appropriate for this data. So those are the two big things. If they ask you to create a residual plot and interpret what you see, we would say in the residual plot, the residuals are scattered with no curve. Both of those are important. They're scattered and that there's no curve, which means a linear model is appropriate. So that's kind of the best case scenario. What we're looking for are potential trouble spots like this. So here's a residual plot where they are not scattered evenly above and below 0, and there's a clear curved pattern in the residuals. And it doesn't matter if it looked like that one does or if it looked like this. The fact that it's a U versus an upside down U doesn't matter. So if we had a residual plot like this, we would say there is a clear curved pattern in the residuals, which means a linear model is not appropriate. So it's kind of two phases. We want to talk about what we see in the data, and what we're mostly looking for is, do you see scattered with no curve or a clear curve? And then we want to say what that tells us about the original data. If there's a curved pattern in the residuals, then the original data is not linear. One more that I didn't put in your notes because it doesn't happen that often, but I just want you to be aware of. Something like this is referred to as a fan-shaped pattern. And just like, it could look like this, where the residuals start small and get big. It could also look like this, where they start big and get small. That's another thing to kind of be aware of. Doesn't mean that the data is not linear, but because all of these residuals over on the left are small, that means for small x values, our scatter or our regression line is pretty close. It's going to make good predictions that are pretty close to the data. But then as x gets larger and these residuals get larger, that means that now the regression line is not as close to the points, and our points are more scattered. So a fan-shaped pattern indicates that a linear model may fit the data okay, but the regression equation is a better predictor for small x values than it is when x values get larger. Or if it was flipped around, it would be vice versa. So I don't think you'll see it that often. The way bigger ones are looking for a curved pattern or looking for a scattered, not curved pattern where it's unstructured. But this is another possibility. All right, so then the next thing is actually not if you have the data. This is a case where if instead of giving you the data, they just give you a couple of values about a set of data. So if maybe the data lists are so humongous that they're not going to give you every single data point that you have to type into a calculator, and they only tell you the means and standard deviations of each of the lists and the correlation. And so our textbook has these formulas. So this is what you're going to copy down into your notes or jot down somewhere in your notebook, or if you're doing the online notes. I just want to let you know that our formula sheet, if you look at the bottom of your calendar or one of the formula sheets I've handed out, they're slightly different because instead of A and B, they use B sub 0 and B sub 1. B sub 0 is like A, that's the y-intercept. B sub 1 is like the slope. And basically what we do is we fill in the correlation and the standard deviation of y over the standard deviation of x, and when we crunch all that out, that gives us the slope of our regression equation. Then once we have the slope, then we can do the y-intercept. Notice that we need to use, whoops, I forgot the subscript on that B there. We actually need to get the slope in order to calculate the y-intercept. But then once we have the slope, then you take the average of the y's, the y bar, minus our slope that we calculated up here, times x bar. And so that's there are going to be some problems that we're going to see in the homework and on the test where either in symbols, so they actually use x bar, y bar, sy, sx, or in words where they just say the standard deviation of this variable is this and the mean of this variable is that, and you have to kind of fit them in. But we'll do some practice with those in a minute. There's one fact that's always true. A least squares regression line will always pass through the point x bar comma y bar. And if we have some time, I can show you the derivation and the formulas of why that happens. The reason I bring it up is because it has come up in a couple of multiple choice questions. Not often, but over all the years that I've seen that they've released the multiple choice, it's come up a couple of times that a regression line always passes through the two means. So I just wanted you to be aware. Oh yeah, the reason why we're not going to talk about now, we don't need it in the video. At some point in class, we might go through it, just so you've seen it. And for math majors, it's good to kind of see what how they would derive a formula like that. We are going to tackle this example. So data was collected from a company that manufactures LCD TVs. We would like to predict the price in dollars of a television based on its screen area in square inches. So a couple things we know already. We know our y variable and our x variable because they told us we are trying to predict price. So that means price is y. We know that y is price because that's what we are trying to predict. And we know that we are basing it on screen area. So then screen area is my x variable. Okay, and so then when they start talking about the means and the standard deviations, we just want to keep that in mind. The mean television price, so that's price, that's a y variable. The mean price was 407.50, so that's the mean of the y's, with a standard deviation of 166.76. So my y bar is 407.5, my x bar is 166.76. The mean screen area, which is my x, was 392.33, so my x bar is 392.33 with a standard deviation of 212.15, so my SX is 212.15, and the correlation for the two sets of data was 0.979, so that is my R. We need to use that information to find the slope and the y-intercept. So here are our formulas. We already figured out that our x variable was screen area and our y variable was price. So I want you to take those and fill in R, SY, and SX and compute the slope. And then fill in the y bar, the slope that you get, and the x bar and see if you can get the y-intercept. And then the one other thing is once you get those two numbers, don't forget to go back and write the equation. Okay, so I want you to practice, pause the video, practice that now, and then you can review. So here is what we should get. Our slope value would be 0.979 times 166.76 divided by 212.15, which should be around 0.77. If you round slightly differently, that's okay. Then my y-intercept, I would take the y bar, 407.5, minus this slope I just calculated, times my x bar. It gives me 105.41. Then that gives me a final equation of y hat, don't forget the y hat, equals 105.41 plus 0.77x. Okay, so then there's a couple other things that we can fill in our notes that I want you to kind of be aware of, and then I'm going to show you a couple things of the graph or questions you might see. So first, an outlier is an observation that lies outside the overall pattern of the data. So if you have a scatter plot, it's kind of going, that's got a positive direction. An outlier is one that kind of breaks that pattern. Is kind of the general way we would define an outlier. Outliers generally have large residuals, and that's one of the ways that they stand out. A point with high leverage is one whose x value is far from x. So in a physics sense, if you have something with high leverage, that means with a little bit of movement or a little bit of effort, you can cause a large change. So the leverage isn't a major term in statistics, but it is one that comes up in this chapter. And if you have an x value that's very far away from the rest of from the x bar, that point will have high leverage. Our regression line has to pass through that point x bar, y bar. That's a fact that we already mentioned. Hopefully you've jotted down as true. So if you have a point whose x is really far from x bar, I don't know why my bar disappeared there, then it really pulls the lines toward it. I kind of think of the example, like if you have a huge group of people like gathered together at a party or just hanging out somewhere, a point with high leverage is somebody who comes in and draws a lot of attention to themselves. I think about them having an x value is far from x. Usually they're doing something outlandish, either in behavior or just the way they are. That draws a lot of attention toward them, and kind of the crowd and all the attention goes toward them. That's kind of like a point with high leverage. If x bar is if you think of x bar, y bar is kind of like where everybody else is, kind of the middle of the group, and all of a sudden you have this point that's way off to the side, kind of acting crazy. It draws all the attention toward it. That's kind of like a point with high leverage. A point is often referred to as an influential point if removing it would markedly change the results of the calculation. So if you have a data point instead of data, and if you remove it, and now all of a sudden there's a big change in correlation, and it might get much higher or it might get much lower depending on the specific point. That point is called an influential point. And then kind of putting the two ideas together, influential points with high leverage can be tough to see in the residual plot, because part of a point having a high leverage is that it actually pulls the line toward it. And so you wouldn't be able to tell just by looking at like the values of the residuals. That's why in general it's always good to look at both your scatter plot and your residual plot, because then between the two you kind of get a full picture of what's going on. And then just one other piece, and next week we'll look at these some more too. But extrapolation is using a regression line to predict outside the range of the data. And the main thing you need to know is that extrapolation is not advised because it's often inaccurate. So for example, if we were to try and make predictions about, like if we were to look at the population for a certain area over the course of 10 years, and then try and look at what we think the population might be 20 years from now, that's called extrapolation, because we only have data for the most recent 10 years. And if we're trying to make predictions outside that range, they're often very inaccurate, because we don't know if the same model will hold. There might be something else that influences the situation. So in general, extrapolation is not advised. We should only make predictions within the range of our x values. And so just a couple of questions, or just a couple of things to point these out. Looking at this scatter plot, so we have a scatter plot that has a positive direction. Couple of questions to be aware of, or that you might be asked, or that you should kind of have an idea of how to tackle is, what if we remove point A? If we remove point A from the scatter plot, what would happen to the correlation? What would happen to the slope of the regression line? Well, the correlation is actually going to go up, because if this point is gone, now we can draw a line that gets really close to all of those. Whereas right now we have a line that kind of is adjusting for this one, but it's also got to get all these other ones. So this point being there lowers the correlation. If we remove it, the correlation would go up. The slope is a subtler thing to see, but if we were to remove that point, my new best fit line would probably shift somewhere down here, and I don't know exactly. Somewhere down here. And if we look at the slope of these two, the new one actually has a steeper slope. The slope is actually going up, because over on this end we can line it up closer to these points but still get close to this one out here. So for one, if we removed point A, removing point A would cause the correlation to go up and the slope to get steeper, to the slope to go up. On the other hand, if we removed point B is one of those points that we say it has high leverage, because its x value is not very close to where the heart of the x values is. And that one is actually probably pulling the line toward that a little bit, which also makes the correlation seem a little bit stronger than it is. So if you removed point B, the correlation would actually go down, because now you have this best fit line We have this one that's kind of far away now. That's going to probably have a bigger impact on the correlation overall. So correlation would go down. The slope is a little bit harder to know exactly, but now that regression line is probably going to come through somewhere in here to try and compensate better for A as well as the rest of these points. So the slope is probably going to get less steep. And actually here we can look. Here's the original data. If we remove point A, the correlation jumps from 0.6 to 0.9, and the slope goes from 1.06 to 1.43. Whereas if we put A back but then remove B, correlation drops from 0.6 down to 0.3, and our slope goes from 1.06 up to 0.592. So it does drop. So generally they would only ask you about points that are pretty clear cut. They're not going to ask you about really subtle points of what would change, but that's kind of the idea of what they'd be looking for in a question like this. Then the last thing left is to look at some computer output. This is from a program called Minitab. It's just one of the computer program outputs you might see. The main thing we want to do right now is to be aware of which numbers you need to know and which numbers you don't. Okay, so first, over on the left, if you look, no matter what data set you're looking at, one of these two lines is going to say the word constant. And it won't always be the top one. Sometimes the output's jumbled around a little bit. The constant, that everything that's in that line has to do with the y-intercept, because that is the constant in a linear equation. The other line is going to have a label that has to do with the variables in the problem. So like in this problem, they're looking at predicting fat gain based on their non-exercise activity. That's what NEA is. And so everything to do with the other line has to do with the slope. And this first column says COEF, which stands for coefficient. So basically this is the coefficient of the constant part of a linear equation, and this is the coefficient of the slope part of the equation. So from computer output, those are these two values. The slope is negative 0.0034415. The y-intercept to be 3.5051. For right now, that is the only thing you need from that top part. Later on, we'll look at a little bit more of that, but for now, that's all you need. The S value is the S we talked about before, the standard deviation of the residuals. And then R-SQ, that stands for R squared. We never use this R squared adjusted value, so don't worry about that. So one of the things we would need to be able to do is to look at an output like this and figure out what is the equation, the least squares regression line for predicting the fat gain for an overfed person based on their non-exercise activity. And so we're just pulling the values weight from here. So I would say that it's y hat equals, let me get my hat on there, a plus bx. So for us, the a is the y-intercept, that's the 3.5051, plus our slope. And you wouldn't have to keep all those decimals. I am for now just because they gave them to me and it's for accuracy. But that would be the equation of my regression line. Then if they said, what is the percent of variation in fat gain that can be explained by the least squares regression equation from part A? Well, that is pretty darn close to that statement that we talked about yesterday that you should be working on memorizing for R squared. In this problem, it's 60.6% or 0.606. If I want to get the correlation, well, first of all, I need to take the square root to get the value. Oops. So take the square root of 0.606. So my R, my correlation value is going to be 0.778. Say 778. The catch is it positive or negative? And here they didn't give us a description to tell the difference. So we got to find some other way to decide whether R should be positive or negative. It's based on the slope. whatever the slope of your regression equation is, that's not going to have the same value as correlation, but the slope and the correlation always have the same sign. So if slope is negative, my R will be negative. And that will wrap up our notes for Chapter 3. So you're all set and ready to do all the book assignments. Next week we'll do a lot of talk and work and practice, and then get ready to test. Have a wonderful weekend.